Hello, Professor and fellow alumni. Michael David here. Today, I am presenting my walkthrough for assignment 4.2, Autonomous Drone Pathfinding and Obstacle Avoidance Simulation. In this project, I developed an autonomous navigation framework modeled on commercial round-trip payload delivery, incorporating hybrid A** search dynamic sense and void collision handling and battery telemetry tracking. Let's dive straight into the code, execution, and simulation runs. I'm executing a clean restart and run all in Google Colab to demonstrate that our entire pipeline compiles deterministically from scratch. The notebook internalizes the workspace, imports NumPy, matplotlib, and our supporting libraries, and prepares the 20 by 20 grid environment without relying on cached data. As the notebook executes, it compiles our core navigation architecture. Global trajectory planning is handled by an A-graph search using an admissible Manhattan distance heuristic, perfectly matched to our orthogonal four-way movement grid. Controlling the mission lifecycle is our four-phase finite state machine, which governs the outbound delivery run, payload drop, inbound, return transit, and emergency fail-safe aborts. During transit, our active sense and avoid layer monitors forward coordinates if a moving hazard enters the drone's planned flight corridor. The system immediately recalculates an alternative route, deducting a 2% computational battery penalty, in addition to our standard half present population drain per step. In the terminal output below, the batch generator is actively compiling and exporting all 6 tests configurations directly to MP4 format. Our baseline clear airspace, our blocked urban wall, low, medium, and high dynamically hazard fields, and our low voltage emergency abort. Once the 6 simulation runs complete, our telemetry model aggregates the performance data, logging step counts, compute latency in milliseconds, collision avoidance, reroutes, and remaining battery percentage. Immediately following plot generation, our automated Git script stages the rendered MP4 video, the updated notebook, and the benchmark infographic, pushing the full build directly to our remote GitHub portfolio repository on our main branch. Switching over to GitHub, we can verify that all project deliverables synced successfully. Inside the assignment 4.2 folder, we have our committed Jupyter notebook, the high resolution telemetry chart, and all 6 MP4 simulation renders ready for review. Now let's open up the exported MP4 video files to explain the drone trajectory behavior across each operational test scenario. Our first simulation tests the low voltage emergency fail safe. The drone launches with an initial charge of 45% as it maneuvers toward the delivery point, and an active obstacle evaluation bring battery reserve down to 39%. The state machine immediately triggers emergency RTB overrides. Go back to base coordinate 00 and land safely with battery remaining, preventing the drone from running out of power mid-transit. Next is our baseline clear environment across 40 static obstacles with 0 dynamic hazards. The drone calculates an optimal outbound path, drops its payload at coordinates 1919, shifts into the returning state, and completes the full round trip in 76 steps, touching down with 62% battery reserves. In scenario 3, we evaluate entrapment within a dense urban landscape featuring 65 static obstacles, and a solid vertical wall at column 12. On frame 0, the initial A search exhausts its open set without finding an open corridor. The system asserts an immediate abort before takeoff, preventing 100% battery capacity by avoiding an impossible mission. Scenario 4 puts our sense and avoid logic under heavy stress with 15 dynamic hazards, exhausting random walk movement. Drone actively recalculates its path 6 separate times mid-flight, navigating around dynamic collisions and completing the delivery cycle in 88 steps with 54% battery remaining. In scenario 5, we lower hazard density to 4 dynamic obstacles. The drone executes a single mid-air evasion maneuver, completing the round trip in 78 steps with minimal processing latency and 62% remaining battery. Scenario 6 tests moderate airspace clutter with 8 dynamic hazards. The system executes 3 mid-flight reroutes, maintaining balance, evasion, efficiency, and landing safely with 57% battery. Back in Collab, this combined benchmark infographic consolidates our experimental results. The blue bars represent computational latency in milliseconds, while the red dashed line tracks collision avoidance reroutes. As hazards density increases from baseline to high search latency, scales nonlinear from 8.4 milliseconds up to 48.9 milliseconds. Combined with our telemetry data, these results demonstrate that our hybrid A Pathfinder, dynamic sense, and avoiding logic and fail-safe state machine deliver robust, energy-aware, autonomous navigation. Thanks for watching.